Good evening, everyone. In previous lecture, we all studied about the first order, first degree differential equation. Now we go for higher order degree differential equation, such as linear differential equation. First, we discuss about how to define linear differential equation with constant coefficient. Linear differential equation are those equations in which dependent variable and its derivative occur only in the first degree and are not multiplied together. Thus, the general form of linear differential equation of nth order is of the form a0 d raised to ny upon dx raised to n plus a1 into d raised to n minus 1 y upon dx raised to n minus 1 plus a2 d raised to n minus 2 into y upon dx raised to n minus 2 plus and so on plus an y is equal to f of x. We consider as equation 1. In this equation 1, a0 is always not equal to 0 and a1, a2, a3 and so on up to an are all constants. In this equation 1, in right hand side, the function f of x, this function is called as function of x only or constant. So equation 1 is called as linear differential equation with constant coefficient. In this equation 1, we use the operator capital D is equal to d by dx. So equation 1 become a0 d raised to ny plus a1 d raised to n minus 1 y plus a2 d raised to n minus 2 y plus and so on plus an y is equal to f of x. This step can be written in the form of in bracket a0 d raised to n plus a1 d raised to n minus 1 plus a2 d raised to n minus 2 plus an bracket close into y is equal to f of x. Here we use the polynomial in D. This polynomial in D is called as auxiliary equation and it is represented by f of D. So in this step, we replace the term a0 d raised to n plus a1 d raised to n minus 1 plus a2 d raised to n minus 2 by f of d. So we write the linear differential equation in the form of f of d of y is equal to f of x. It is called as equation 1. Here the equation 1 and equation 2 both are called as linear differential equation with constant coefficient. Now we discuss about the how to find out the solution of this linear differential equation. The solution of linear differential equation can be divided into two parts. Number one is complementary function and second one is particular integral. You are always remember complementary function of this equation is finding with the help of left hand side. That is, complementary function is totally depend on the which type of the roots of the given differential equation, and particular integral is totally depend on right hand side, that is which type of function is present in the right hand side. And most important thing we discuss with all of when the f of x is equal to 0, then given equation is called as homogeneous differential equation, and if f of x is not equal to 0, then it is known as non-homogeneous differential equation. Up to this part, we discuss how to define linear differential equation, how to write the solution of linear differential equation, what is the difference between complementary function and particular integral. But now we discuss the rule for finding the complementary function. There are mainly 4 cases for finding the complementary function. First we discuss the case number 1. In this case number 1, when roots are real and different, then how to find out the general solution? First we consider the m1, m2, m3, m4 and so on mn are the n roots and all our roots are real and different. That is, m1 is not equal to m2, m2 is not equal to m3, m1 is not equal to mn. Then the general solution of the f of dy can be represented by y is equal to c1 e to the power m1x plus c2 e to the power m2x plus and so on cn e to the power mnx. In the general solution, c1, c2, c3 up to cn are the constant term and m1, m2 up to mn are the real and different roots. Second one case, in that case when two roots are real and equal, we consider m1 and m2 two roots and these two roots are real and equal. Then general solution is can be written by y is equal to in bracket c1 plus c2x bracket close multiply with e to the power m1 or m2x. But when three roots are real and equal, then how to find out the general solution? For this purpose, we consider the three roots m1, m2, m3 and m1 is equal to m2, that is m2 is equal to m3, m1 is equal to m3. Then we define general solution by the formula y is equal to in bracket c1 plus c2x plus c3 x square bracket close multiply with e to the power m1 or m2 or m3 x. When n number of roots are real and equal, that is m1 is equal to m2 is equal to m3 is equal to m4 and so on is equal to mn, then general solution of f of dy can be represented by y is equal to in bracket c1 plus c2x plus c3x square plus and so on cn x to the power n minus 1 bracket close e to the power m1x. But in case number 5, we discuss when roots are imaginary, such as alpha plus minus I beta. When we given the root like imaginary alpha plus minus I beta, then we write the general solution in the form of y is equal to e to the power alpha x in bracket c1 cos beta x plus c2 sin beta x. Case number 6. In that case, we discuss about when roots are repeated imaginary. Such as, suppose we consider m1 is equal to alpha plus I beta and m2 is equal to alpha minus I beta, twicely repeated imaginary number, then general solution of the f of dy can be represented by y is equal to e to the power alpha x in bracket c1 plus c2x multiply with cos beta x plus in bracket c3 plus c4x multiply with sin beta x. In this way, we find the complementary function by using this number of cases. In short way, we discuss about how to find out the complementary function. Listen here. There are 4 types. First type is when roots are real and different. Second is when roots are real and equal. Third one is root are imaginary. And fourth one, roots are imaginary but repeated. For all these cases, we find the general solution. Thank you.